For nearly a century, earthquakes kept revealing something they were never supposed to find.
Not once. Not twice.
But over and over again. The signals were only slightly different. Small enough to ignore. Easy to blame on imperfect instruments, or difficult mathematics, or simply bad luck. That explanation worked. Until it didn't. Every new earthquake became another opportunity for the anomaly to disappear. Instead, it kept coming back. The earthquakes came from different parts of the world. The recording stations were separated by entire continents. The wave paths were never identical. Yet the same unexpected delay appeared again and again. Eventually, the investigation stopped asking whether the measurements were wrong. It began asking a far more uncomfortable question. What if the picture of Earth's interior was wrong instead? The Earth's interior is hidden beneath nearly 3,000 kilometers of rock. Every picture scientists build depends on interpreting faint seismic vibrations. Small uncertainties are part of the job. Looking deep inside Earth is unlike taking a photograph. No one has ever seen the lower mantle. Every image is reconstructed from faint seismic vibrations. Small uncertainties are expected. But this pattern survived them all. Every time certain waves skimmed the deepest part of the mantle, they slowed in the same two places. The pattern refused to disappear. Instead, it became sharper. Years of measurements accumulated into millions of recorded travel times. Independent seismic networks kept adding new observations. Each new earthquake became another witness. Every new earthquake had a chance to make the anomaly disappear. None of them did. Instead, each one made it harder to dismiss. The familiar cross-section of Earth began to change. The smooth mantle that had filled textbooks for generations no longer matched the evidence. Two immense regions slowly emerged from the data. One beneath Africa, the other beneath the Pacific Ocean. No one had drilled that deep. No camera had ever seen them. Their outlines existed for one reason only. Earthquake waves kept tracing the same hidden shapes, again and again. The investigation was no longer asking whether the signals were wrong. It had become something far more difficult. What could possibly occupy the same two enormous regions inside Earth every single time an earthquake looked their way? The simplest explanation wasn't that Earth was hiding something. It was that the picture was wrong. If the mathematics behind those reconstructions were flawed, the hidden regions might simply be artifacts created by the models themselves. The only way to test that possibility was to rebuild the planet from scratch. Again. And again. Research teams around the world approached the problem independently. They used different earthquakes, different seismic stations, different collections of wave paths, different mathematical techniques to reconstruct the same inaccessible interior. If the hidden regions weren't real, this was where they should have disappeared. They didn't. One reconstruction revealed a vast province beneath Africa. Another found it in almost exactly the same place. A third recovered both structures with different data. Then a fourth. The details varied. Their edges shifted slightly. Their heights were refined as better observations accumulated. But the overall picture refused to change. Beneath Africa sat one immense, low-velocity province. Beneath the Pacific lay another. Independent investigations were beginning to describe the same hidden landscape. The evidence did not stop with tomography.
Researchers turned to another witness.
Instead of asking only when seismic waves arrived, they examined how the waves themselves changed shape after passing through the deepest mantle.
Some waves split. Others bent.
Some arrived stretched and distorted in ways the surrounding mantle alone could not reproduce. Those distortions appeared along the same boundaries already outlined by the global maps. The two lines of evidence had been developed independently.
Now they were pointing to the same places.
The transparent cross-section of Earth returned once more. The faint shadows that had first appeared as suspicious anomalies had become sharply defined structures anchored above the liquid outer core. They were no longer surviving because one model predicted them. They survived because completely different observations kept finding them. The investigation quietly crossed an irreversible line. The question was no longer whether these hidden provinces existed. Only one question remained.
What made them different from everything surrounding them?
Heat looked like the answer. For a while, hot rock slows seismic waves. That has been understood for decades. If those two hidden provinces were simply hotter than the surrounding mantle, the mystery would almost solve itself. The idea fit the observations. At first, researchers built computer models of Earth's interior, allowing hotter regions to rise and cooler material to sink through the mantle. The simulations produced slower seismic waves, just as expected. For a moment, the investigation appeared to be settling into an ordinary explanation. Then, the evidence began to disagree. The first contradiction came from the provinces themselves. Their edges were too sharp. As seismic waves crossed from ordinary mantle into the hidden regions, their speeds changed over surprisingly short distances. In some places, the transition occurred across less than 100 kilometers.
Heat does not usually behave that way.
Temperature spreads gradually through solid rock. A purely thermal boundary should fade from one state into another.
These did not.
They rose from the core like enormous cliffs hidden inside the Earth. The sharper the seismic measurements became, the more abrupt those boundaries appeared.
The simple answer had reached its limit. The evidence kept going.
If temperature was no longer enough, something inside those provinces had to be physically different. Researchers turned to a completely different witness. Occasionally, an enormous earthquake does something remarkable. Instead of sending only traveling waves through the planet, it makes the entire Earth vibrate. For hours, sometimes even days, the planet rings like a bell. Those faint global vibrations carry information that ordinary seismic waves cannot. They are sensitive not only to how fast waves travel through rock, but also to how mass is distributed deep inside the planet. When researchers compared those planetary vibrations with their models, another pattern emerged. The hidden provinces were unlikely to be composed of ordinary mantle alone. The best-fitting models suggested they were also slightly denser than the surrounding rock. Not dramatically, just enough to matter. That single result changed the investigation. Hotter rock can slow seismic waves. Hotter rock alone does not naturally become denser. Now, two independent observations had to be explained together. The provinces slowed seismic waves, and they appeared to contain more mass than the mantle around them. The transparent cross-section returned once again. The two giant provinces remained exactly where they had always been, but they no longer looked like warm patches drifting through the mantle. Layer by layer, new evidence settled onto the same shapes. Sharp boundaries, greater density, long-term stability. The map itself
had not changed. Only its meaning had. The investigation was no longer searching for unusually hot rock. It was searching for reservoirs that seemed to have preserved a different physical identity for billions of years. And that raised a far more difficult question. If these enormous structures were made of different material, where could that material possibly have come from? For billions of years, Earth's mantle has never been still. Hot rock rises. Cooler rock sinks. Entire ocean floors descend back into the planet through subduction. Deep currents slowly recycle enormous volumes of material, reshaping the interior over geological time. If the hidden provinces had formed early in Earth's history, there was an obvious problem. Why hadn't they been mixed away? Researchers turned from seismic observations to another kind of evidence. Not measurements from earthquakes, but physics. Computer models recreated the slow circulation of the mantle over billions of years. Every simulation began with the same question. Could structures this large actually survive? Many could not. If the hidden provinces were made only of ordinary mantle, heated above their surroundings, convection eventually stretched them apart, dispersed them, and erased their identity. The models repeatedly arrived at the same conclusion. Heat alone could not preserve continent-scale structures for nearly the entire age of the Earth. Something else had to anchor them. When researchers allowed the simulated provinces to contain material that was slightly denser than the surrounding mantle, the behavior changed dramatically. Instead of being swept away by convection, the dense material settled naturally above the liquid outer core. The provinces deformed. Their outlines evolved. But they endured. For billions of years, they remained remarkably stable. For the first time, the simulated mantle began to resemble the seismic maps. The investigation had crossed another threshold. The question was no longer whether chemically distinct reservoirs could survive. Physics showed that they could. The question became where that dense material had originated. Several possibilities emerged. One proposed that the provinces were among the oldest surviving parts of Earth itself. During Earth's earliest history, a global ocean of molten rock slowly cooled and separated into different chemical layers. Some researchers suggested that dense remnants from that ancient differentiation had never completely mixed with the rest of the mantle. Instead, they settled near the core and remained there ever since. Another possibility looked much younger. For hundreds of millions of years, oceanic plates have carried dense crust back into the mantle through subduction. Over immense spans of time, that recycled material could accumulate above the core, gradually building the massive provinces revealed by seismic waves. Both ideas could reproduce important parts of the evidence. Both remained physically plausible. Neither explained every observation on its own. Then the investigation expanded beyond the Earth itself. Not because the seismic maps demanded a dramatic story, but because another branch of planetary physics had quietly reached a surprising result. Then an entirely different field arrived at the same question. Not by studying earthquakes, by reconstructing the birth of the moon. Not every fragment from the collision disappeared. Under certain conditions, portions of the impactor's iron-rich mantle remained denser than Earth's own. Instead of mixing completely into the young planet, those fragments sank. Slowly. Relentlessly. Until they reached the boundary above the liquid core. The simulations produced continent-scale reservoirs in the same region where seismology had already mapped the hidden provinces. It was an extraordinary correspondence. But only a correspondence. The simulations demonstrated that such structures could form this way. They did not demonstrate that they had. The transparent Earth appeared once again. The mapped provinces did not move. Only the interpretations surrounding them multiplied. One layer represented ancient primordial reservoirs. Another represented billions of years of recycled oceanic crust. A third showed dense fragments from the moon-forming impact. The observations beneath them remained exactly the same. For the first time, the investigation separated what had been measured from what was being reconstructed. The map was no longer under debate. Only its history was. Every investigation reaches a point where the evidence becomes more valuable than the explanation. This was that point. The earthquake waves had established the existence of the hidden provinces. Independent seismic reconstructions had confirmed they were real. Waveform studies had traced their sharp boundaries. Global vibrations had suggested they were slightly denser than the surrounding mantle. Mantle physics had shown that heat alone could not account for everything being observed. And planetary simulations had demonstrated that material from the moon-forming impact could survive in exactly the part of the Earth where those provinces now reside. No single discovery solved the mystery. Together, they made the simpler explanations harder to keep. That distinction became the most important result of the investigation. The transparent cross-section of Earth returned one final time. Nothing about its shape had changed since the previous movement. Two immense structures still rested above the liquid outer core. One beneath Africa, one beneath the Pacific. This time, however, the observations and the interpretations no longer occupied the same layer. The mapped provinces remained fixed. Above them appeared only the properties directly supported by evidence. Slower seismic waves, sharp boundaries, slightly greater density, long-term stability. Only beyond those measured properties did the competing histories begin. One reconstruction traced the provinces back to Earth's earliest magma ocean. Another allowed billions of years of recycled oceanic crust to accumulate into dense reservoirs. A third followed fragments from the giant impact that formed the moon, sinking through the young mantle before settling near the core. Each reconstruction explained part of the evidence. Each left important questions behind. The primordial reservoir model naturally accounted for extraordinary age, but it must also explain how those reservoirs preserved their chemical identity through billions of years of mantle circulation. The recycled slab model fits Earth's continuing tectonic engine, yet researchers continue testing whether enough subducted material could accumulate into structures of this scale while matching the observed seismic properties. The giant impact model offers a physically demonstrated pathway for dense foreign mantle to survive. But the simulations remain exactly that. A physically viable reconstruction, not a direct observation of Earth's past. No single explanation has eliminated the others. Instead, decades of research have steadily narrowed the range of possibilities. The investigation did not end by identifying one perfect history. It ended by defining the limits of what the evidence can honestly support. The strongest conclusion is also the simplest. The large low-shear velocity provinces are real. Their existence no longer depends on one instrument, one earthquake, one research group, or one computational model. Multiple independent lines of evidence converge on the same deep structures hidden nearly 3,000 kilometers beneath our feet. What those structures are has become increasingly constrained. What they ultimately came from remains an active scientific investigation. The transparent Earth appeared one last time. The hypothesis overlay slowly disappeared. The simulations faded. The competing reconstructions dissolved. Only the measured planet remained. Beneath Africa. Beneath the Pacific. Two continent-scale structures, traced not by drilling or direct observation, but by countless earthquake waves that crossed the same hidden paths over decades. Nothing about those structures became less remarkable when the speculation was removed. If anything, they became more so. Because regardless of whether they prove to be primordial Earth, the accumulated remains of ancient oceanic plates, or surviving fragments of the world that helped create the Moon, the measurements themselves do not change. Deep inside our planet, the evidence has been waiting all along. Earthquake after earthquake. Wave after wave. Quietly rewriting the map of the Earth from the inside out.